Morning. Today I am going to discuss the second part of random signals, and I told you that the random signals are power signals. I have explained why, and I am going to discuss about properties of autocorrelation function of a random process, cross correlation function, and I am going to do some MATLAB simulations also. Okay, so let us start with the autocorrelation function. You know the definition of autocorrelation function here is the RXX of t comma t plus tau. So this total thing can be replaced with only tau because t is insignificant here. Okay, is a RXX is a function of tau that is equal to expected value of the x of t and delayed x of t. Okay, at another time, at two different time locations separated by tau. So that is what I have to take the ensemble average, and that I will call it as a autocorrelation function of the random process. Okay, so this I already discussed. Now the properties. Let us talk about the properties. The properties are almost similar to the autocorrelation function of deterministic signals, but here only the expectation operation will be there. It is ensemble operation basically. Ensemble operation. Otherwise, more or less they are similar, except at 1 or 2 points they are different. And here, so I am taking the autocorrelation function of a random process like this. This is tau equal to 0. So this will be something like this. It will look something like this. Okay, it will look something like this. And at tau equal to 0, it reaches the maximum. So this is RXX 0. Okay, so this is RXX tau. Okay, so the peak value occurs at the center, and that is equal to the expectation of x square. So what is x square? X of t multiplied by x of t. So here, that is because when I see this is the expression for autocorrelation function, I am substituting tau equal to 0. So that is r of 0. So tau equal to 0 is x of t multiplied by x of t, x square of t. So if I take the average, especially the ensemble average, so that is nothing but here ensemble average, that is nothing but r of 0. That is at tau equal to 0, whatever value is there, that is nothing but the mean square value. This is nothing but the mean square value. Okay, so this is nothing but the mean square value, and that is also nothing but total power. Okay, that is also nothing but total power. If I assume that the mean of this process is 0, so what is total power? Total power equal to constant power DC power plus AC power, alternating. I mean, that means variable component plus constant component. So these are the DC power plus AC power. So if I take mean value 0 for the process, this DC becomes 0, I have only the AC power. So then that AC power is nothing but, what is that you can call? You can call that as variance. That is variance. Variance, you know, by famous symbol, that is sigma square, sigma x square, because x is the random process. So here, it is basically the these are all ensemble values. You should see. You should not take single waveform and see. You have to take the multiple sample functions, multiple time functions, then find it and average it. So that is how you get this. Okay. So this is a constant value. Variance is a constant value. Total power is a constant value. And if the mean equal to 0, that is variance. Otherwise, you have some DC component also plus constant power. Okay, DC power. That is total power. And that is the total power, which is nothing but the mean square value. Okay. So at the center, single value, whatever I have at the center at tau equal to 0, this value is nothing but the total power. Okay. So that is the first property. Second property, the autocorrelation property, the autocorrelation function of a random process x of t is maximum at the origin, that is at tau equal to 0. It is the maximum. That means at any other value, if I take any other value here, this side, here, or this side, any side if I take, so it will be less than that one. Okay. It will be less than that one. So it can be mathematically, it can be shown, it can be written that modulus of, that means here I am taking, negative value or positive value. Both I am taking here. Okay. So because sometimes the autocorrelation can be minus also. For some points it may be minus also. That's why you take absolute value, and especially because in general if I take, I will take the complex signal. So for that you have to take the modulus of that one. Okay. So absolute value of this is absolute value of autocorrelation at tau. That means any tau. This is tau. Here tau, I should say not equal to 0. Okay. This tau here means it is not equal to 0. So here 0 is there. Okay. Of course here this is equal to sign is also there. I can, this for example, let us say I will remove this. I will remove this one. Okay. Then for tau equal to 0, it is maximum value, right hand side. At tau is not equal to 0, this is always less than this value. Okay. It is less than this. Yeah. I think you can include, you can include the sign also, no problem. So it is, you can include that. Okay. So that means the maximum, the peak of the autocorrelation function occurs at the origin, that is tau equal to 0. So this property is also same for the deterministic signals. Now the autocorrelation function of random process x of t is an even function of tau. That is rxx minus tau equal to rxx of tau. Okay. So what it means is, it is basically lateral inversion. So this is what exactly. If this autocorrelation function is like this, then what is mirror symmetry? It will be approximately like the same shape. It is the mirror image basically. Okay. So that is what you have here. This is the lateral inversion also, or mirror image, or even symmetry. That is also same for deterministic signals. Also it is same. Now fourth property. If x of t is a random process, now having non-zero value, that is expectation of x of t is not equal to 0, because mean value is not equal to 0 for the total process. Okay, that is more important. Sometimes if I take a sample function, the mean may not be 0. But when you take all sample functions and all means, again you find the average value of all means, you will get that value. Okay. So it is basically, when I say this one is the total property of the process, not the property of a single time function. Okay. So here mean is not equal to 0, non-zero mean, and ergodic with no periodic components. And it is ergodic. That means time averages are equal to ensemble averages. So if I take autocorrelation function I can find autocorrelation function for each time function and take a average of all those things. Okay, so that is one thing. Then I can take vertically variable for that autocorrelation function I can find. Again, like that for different things vertically. Again, I can average the autocorrelation functions. Okay, so if the autocorrelation function is same whether you take vertically or horizontally, then you can call it as an ergodic process. Okay, ergodic process means ensemble averages are equal to time averages. Okay, that's why this I have already discussed with you. So we are assuming that x of t is a random process with non-zero mean and it is ergodic and no periodic components. That means totally stochastic component. There is nothing but random component. Okay, there is no periodic signal. So in that case, what happens is, let us take this. This is the peak value. It will reach some steady state like this. I mean, this I am zooming here. This much may not be there. Very small pedestal will be there here. So this is nothing but x bar square. Okay, what is x bar? Ensemble, I mean expected mean, ensemble average, and that is vertically, that is x square. So this is, so as tau tends to infinite, it is modulus of tau. That means both sides, minus infinite plus infinite, both here. This is 0, this is tau axis 0, this is plus infinite, this is minus infinite. So both asymptotically, what happens here is the value of the autocorrelation function at infinite asymptotically, it becomes constant. That is what is. Okay, so that is the constant. So that is nothing but mean value, square of the mean. That means this is nothing but DC power. We see, I am not calling as a DC energy. It is a DC power because random signals are nothing but power signals. Okay, that we have seen already. So this is the DC power. This is non-zero mean. That's why we called it as a non-zero mean. If it is zero mean, this will be 0 automatically. For 0 mean, it will be 0. Okay, otherwise it is not 0. It is equal to the square of the mean. So this is a very important character which is not there for energy signals. Okay, so this is basically asymptotically it reaches our pedestal. So this is the fourth property. Then fifth property is, if x of t is periodic, it is a random process, but it is periodic. That means each sample function or time function is also periodic. That means it contains a deterministic component and stochastic component. Both it has. Okay. So, for example, if I take that kind of thing, let us say something like this. Okay. I'm not exactly, this cycle, so it is random basically. So there is a random component riding on a sine wave, for example. Okay. So this is the random component, and the middle value, whatever you have, that is nothing but the deterministic component. So there is a sine wave plus noise is there. That means a random component. So this is, I can say that this is it also has periodic component. This process x of t equal to periodic plus stochastic. Okay, both. It has a periodic component plus stochastic component. Then what happens? Then autocorrelation function is also periodic. So in this case, what happens is, So how it looks, the autocorrelation function? Probably it is a periodic function. So it goes like this, goes like this, goes like this, but this won't be that much plot, of course. Okay, so there may be some kind of, I think even then these oscillations won't be there because you are taking ensemble average. Little will be there. So I will erase this. So these components you can ignore. So it is a periodic one, and because of ensemble averaging, this becomes smooth curve. Okay. It is a periodic one. Okay, it is something like this, something like this. So it is a periodic one. Autocorrelation is also a periodic one. That is the fifth property. Then sixth property, if the random process x of t with zero mean has the DC component d such that x of t equal to a plus x of t. Okay, this is d. I call it as d. So d plus x of t. D is a constant value plus random component is there. Random process is there. Constant value plus random process. So that is what is the total. You can call this as y. This is y. Y of t equal to d plus x of t. That means constant value plus random process. Okay, this is the output process. After adding, I will get the resultant process like this. Then what about autocorrelation function? Then autocorrelation function is the same shape, but d square, the constant value, it will become d square. If the constant value is 1 square is 1. Constant value is 5, it is 25. So how it looks, let us see. See here, if I take so autocorrelation function may be something like this. Something like this. So up to this is d square. Okay, this height is d square. D square plus this autocorrelation function. This autocorrelation function is nothing but this kind of thing. Okay. So basically what happens is when there is a DC component, and I have the random process, the DC component square, that is DC power, that much height, the autocorrelation function raises. Okay, so it rates, the autocorrelation function rates on the DC square value. Okay, that is what is you have the DC power, you can say. So that is what I mean. Basically, this is it acts like a pedestal for this one. When this becomes 0, slowly the autocorrelation function comes down. Slowly it comes down. It reaches this is the x-axis. Okay, 0 x-axis. So it is simple one only. There are 6 properties like this. 7th property is it is basically based on the sum of the 2 random process. I have 2 random process x and y. I am adding these 2 random process. What happens to the autocorrelation function of the resultant process? So z of t equal to sum of x of t and y of t. So x of t has its own autocorrelation function, that is nothing but rxx here. Similarly, y of t has its own autocorrelation function, ryy. Then the cross correlations are there between these two, rxy and ryx. All these put together, they sum up the all two cross correlations two cross correlations and two autocorrelations, they add up to give the total autocorrelation function of the summation process. Okay, so that is this is the typical. I mean, correct. This is because it's only cross terms are also added. So this happens here, okay. And of course there basically even for deterministic signals it might be true, but expectations won't be there. Okay, so here whatever is there here RxX means expectation is included in that itself. Okay, so that is what. So 7 properties we have seen the processes of that. Then cross correlation of x of t, y of t, expectation of x of t multiplied by y of t plus tau. So for every tau you have to do that. Then similarly RYX. So naturally RXY is not equal to RYX. Okay, as usual. So here let us see few properties of that one. X of t and y of t are the two random process, and they are at least jointly wide sense stationary. Okay, second order basically at least second order joint stationary. That means autocorrelation functions. Because we are talking about wide sense stationary process means at least wide sense stationary, at least autocorrelation must be constant. Okay, so here when I see the cross correlation here, RYX tau equal to minus of RXY tau. This is called symmetric property. Okay, and which kind of symmetry this is? This is odd symmetry. Correct? So here for example, if I have this kind of thing, this is called even symmetry. Okay, this is called even symmetry. Odd symmetry means if I have this one, I will be having from this side this one. Okay, so this is plus side, same thing on the negative side. That's why you got the minus here. Okay, so this is I should say odd symmetry. Second property, RxX, RYY are the autocorrelation functions of x of t and y of t respectively. Then the cross correlation function actually here then satisfies the inequality given by this. So what it means is this RxY cross correlation function cannot be more than the geometric mean of both autocorrelation functions, autocorrelation values RxX and RYY at origin. Okay, so what is RxX0? RxX0 is nothing but mean square value of process X. RYY0 is nothing but mean square value means power. So power of y of t. This the other one is power of x of t. So you are multiplying both powers and taking the square root. So this is nothing but geometric mean of the powers. Geometric mean of powers of two processes. Okay, so geometric mean of two processes. So let us take one mean square value, that is power of first process is 24, power of second process is 12. So I want to find the geometric mean. 24 multiplied by 12 and square root. So when I take square root, I got 16.9706. So this is the what is this one? This is the limit, upper bound. Basically this is nothing but upper bound. upper bound. This is the upper bound for what? For this cross correlation function. So a cross correlation function cannot be more than the geometric mean of both powers. That means powers of two random process. Okay, both powers. This is 16.96. So let us see the third property. We will compare this with another upper bound is there. So that is arithmetic mean bound. So here, same thing, the cross correlation function Rxy cannot be more than the mean value of the both powers. That is power of first process and power of second process. Both, if I take mean value, average value of both powers, that is the upper bound. Okay. So there is nothing but arithmetic mean. And let us see in our example, 24 plus 12 divided by 2. So there is nothing but 30. So arithmetic mean is higher than the geometric mean. Okay, in general it will be like that. So arithmetic mean is loose upper bound. I should say that this is upper bound is loose. This is loose upper bound. And this is, other one is, this is tight. So I will write it here. This is tight upper bound. Okay. So geometric mean is the tighter bound. Arithmetic mean is the loose upper bound. That is third property. So here actually this is 30, earlier it was 16.97. So it is tighter. It cannot be more than 16.5. If it is not more than 16.5, automatically it is also not more than 30. Okay. So that means the geometric mean will be satisfied before the arithmetic mean is satisfied. Okay. I mean you can consider like that. And arithmetic mean bound is not a tight bound, it is a loose bound. Then fourth one, if x of t and y of t are two random processes that are statistically independent and at least wide sense stationary. Okay. So these two processes are there, they are at least wide sense stationary process and they are independent process. Then because they are independent processes, Rxy equal to x bar minus y bar. So what it means? It is the product of two means. The cross correlation is the product of two means. And if both have zero mean process, both are zero mean process, then in limit it becomes zero. Okay, because zero mean process. So if you take larger taus, at larger taus, it becomes zero. Okay. So what it means, the cross correlation, what it means, if I have cross correlation like this, cross correlation function between x and y, it is asymptotically, it will zero this side. Otherwise, in general, it won't reach zero, it will reach some pedestal, it will stop there. So what is this value? X bar multiplied by y bar. Product of two means. So here it asymptotically it reaches a constant value. In this case, that constant value is zero. Okay. So that is what you have for both fourth and fifth points. So let us see some simulations. In these simulations, I have generated three sample functions. Three sample functions are time functions of a random process. All these three belong to same random process. So what is that process? It is a Gaussian process with zero mean. If you see these values this side, if you see these values here, this is plus 2, minus 2. So between minus 2 to plus 2 and mean value is 0. Okay. So it is a random signal. random function, time function 1, time function 2, time function 3. 3 I have generated. These 3 come from the same parent. That parent is Gaussian process. Okay. So then what I can do, I can generate 100 or 1000 also like this. Infinite number of sample functions I can generate like this. Now for these 3, these are the 3. So corresponding histograms I am showing it here. See, the samples I took was around 128, I believe. I have put the time axis here, and this is 0.15 here, and this is approximately 0. Which could be 0.17, something like that. Okay, 17, and the width, that is the total duration of the signal. And because I assume some sampling value like that, I have done it well. Okay, so that's why I represent it as a time. As the time progresses, the signal is changing. So that's why it is a random signal, and it is spanning over a finite duration, that is 0.17. Okay, so this is what you have, and histogram if I take. For histogram, on x-axis what will be there? 0, +1. So whatever +1, +2, +3, this side -1, -2, -3. Whatever was there, this is the signal range, correct? Signal range is this. This is the signal range. So whatever signal range is there, this signal range, it will appear horizontal in the, so this is the signal range, expanded one, okay? So this is what is the signal range here, 0 to +3, 0 to -3. So approximately, okay, +3 to -3. So the signal is available. Here also if you see, what is this? This is 0 to, correct? Second waveform. See the second waveform. This is 0, this is 2, and half of this is 3. Okay, this is 3. And similarly this is -3. -3 to +3. So that's why I have here -3 to +3. And I used 50 bins here. So the total range between -3 to +3 is divided into 100 bins. And each bin, how many values are falling? So that is what is the count histogram. So here, if you see, first time function has, the shape is appearing Gaussian shape, but there is no smooth curve like that because the number of samples are small. So these are basically estimations. There are no insufficient number of samples. So for first time waveform, this is the histogram, second histogram, third histogram. All will look similar. That is, globally, when I take global property, if I take something like the smoothing, this and this, these all are same. Okay, so they appear same, but they are not exactly same. Okay, I will come to the ensemble later. So this is what. Now I have taken the autocorrelation function of this random time function. So this is autocorrelation function. This is autocorrelation function. So what is this one? Because it's a random signal, contains all frequencies. So it contains all frequencies equally. That's why it is called, it can also be called as white noise, white Gaussian noise. Okay. So the constant, basically the power is at all frequencies constant. And power contains all frequencies, correct? So all frequencies are there in the signal. All frequencies having equal power. There is a constant spectrum. When I take inverse Fourier transform for that one, I will get a delta function like this. So indication is, if something is wideband, something is wideband or the bandwidth is very high, in the time domain, the support in the time domain will come down, because if the time signal expands, frequency spectrum will compress. If the frequency spectrum expands, time function will compress. So this time function is compressed now. Earlier, if I had taken any pulse or something, it was like that. Okay. Now this shape is compressed towards single delta function. Okay, so these are the second realization, third relation. These are the autocorrelation functions of all the three realizations. Now, take another waveform. That is, okay. Yeah, let us take this. So there are sample function 3 again. What is the range here? 0 to 1. 0 to 1. Actually, I have subtracted the DC value. DC is 0.5. I have subtracted the 0.5 later after plotting that one. And that is what I am using here. So this is between 0 to 0.5. That is the range here, minus 0.5. Because I have generated each value there, subtracted each value by minus 0.5. The DC I have subtracted. So the DC, after subtracting the DC, it contains only variable values around mean value, that is x equal to 0. At around 0 value, positive values plus 0.5 minus 0.5. Earlier it was between 0 and 1. So these are uniform density functions. These uniform density process, basically each one is a density function. They are also almost flat here. Okay. Earlier what was in case of Gaussian, what happened? The bell shape was there. So at higher values, the higher values are occurring rarely, and middle value, mean value is occurring most of the times. So similarly, when I plot the histograms, I have the histograms, I should say constant, uniform. They are almost similar because of data is small. You are appearing like this. Okay. If I increase the data to 10,000, 20,000, you will get a you will get a flat value like this. Okay. So even now, this is the histogram of first sample function, histogram of second sample function, histogram of third sample function. Like that, I can take 100,000 signals, 1,000 sample functions, and 1,000 histograms I will get. So all these histograms, if I average all these things point by point, this plus this plus this, this plus this plus this. So vertically, if you add all these things, then divided by 100. If the number of sample functions used are 100, so after adding these waveforms, you take the average waveform. Basically, it is nothing but average waveform, all 100 waveforms. I have shown here only 3 histograms. You can generate 100 realizations. This is called realizations. Each realization of a random process. Okay, that is nothing but each time function of a random process. So the time function, if I generate a time function 100 times, 100 different time functions, 100 different histograms, so then I will add up and then I will get the very smooth one that is nothing but uniform density function. So this is nothing but uniform density function. Now coming to autocorrelation function, it shows delta function again at the center because it is a very wide band signal, and each sample is totally uncorrelated with the other sample. Okay, so if you take the waveform, see, I will go back to the waveform. See here, these waveform, they are totally random. The first sample is not dependent on second sample. There is no correlation at all. So if there is no correlation, then it becomes uncorrelated random process. Then what is that you will get? You will get the delta function as autocorrelation function. Okay. So if I take Fourier transform for this, what happens? If I take Fourier transform for this delta function, I will get a flat curve like this, flat line. So that is nothing but power spectral density. This is nothing but power spectral density in the frequency domain. So there is nothing but x of f frequency. This is frequency. So this is constant. This height is constant. Okay. So that means this process, random process, contains all powers equally because it is an uncorrelated process. If it is a correlated process, the spectrum will change. Okay. So at this point of time, whatever I have done, they are for uncorrelated random variables. That means random process. Each sample function is totally independent, is totally uncorrelated with the another sample function. So that's why each sample function has autocorrelation function, which has a delta at the center. Okay, so this is what you have. Probably we will because we need spectral densities also. Maybe in the next class I will do some simulations in MATLAB and I will give the presentation to you how the spectra, similar analysis of spectra also. I have to take average spectra there. Here average autocorrelation function I am taking, that is ensemble average. In the frequency domain also I have to take ensemble average. Okay, because it is a sample function. Each sample function has different autocorrelation function except at the center, and accordingly the power spectral density also it will be different for each sample function. But if I average all those power spectral densities, then you will get the smooth curve. So that is nothing but the power spectral density of the random process. Okay. So thank you so much for your time. I am stopping it here. In the next class, we study about something about the power spectral densities of a random process. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.